This is the assembly line balancing example, handout example that is posted on Blackboard. We have these tasks A through G, their predecessors, and the time that it takes each task in minutes. And the first thing we want to do is draw a precedence diagram from the data given. So we start with the tasks that don't have a predecessors. We have task A doesn't have a predecessor. We are drawing an activity on node diagram. The activity is going to be on the node. So A, we start with A because it doesn't have any predecessor. After we do A, we can do B and C. So we draw an arrow and we put B and we put C. After we do B, we can do D and E. So we put an arrow and put D and E. After we do D, we can do F. And after we do C, E, and F, we can do G. So we extend lines to show the predecessor. All these three have to be completed before we can do G. It's also good to put the times on top of the nodes. So A takes 4 minutes, B takes 2, C takes 1, D takes 1, E is 5, F is 3, and G is 4. So this is called a precedence diagram for this problem. We write down what is given, draw and label a precedence diagram that represents the different activities. The line should be capable of producing 120 units in a 10-hour day. So we know that the operating time is 10 hours a day. Since we are given the time for the tasks in minutes, if we want to do everything in minutes, then we have to change this to minutes. So this is 600 minutes. And the demand is 120 units. So in a day, we want to make 120 units. So the idea is to design an assembly line with workstations and assign these tasks to the workstations so that the line is balanced and we can make these 120 units in a day. How do we do that? And this is a paced assembly line, so the amount of time spent at each workstation is going to be the same. That is referred to as a cycle time. So we're going to have to start by calculating the cycle time. Cycle time, CT, is operating time divided by the demand. So that's going to be the 600 divided by the 120. So that's going to be the 5 minutes. Cycle time depends on your operating time and the demand. So if you have an assembly line, what you're saying that every 5 minutes a unit is rolling off the assembly line. Every 5 minutes you are making a unit of the product. So if every 5 minutes you're making a unit of the product, in 600 minutes you're going to make 120 units. So that's the idea. Then we calculate, so that's a known measure for assembly line balancing. The other known measure is called the theoretical minimum number of workstation. In theory, how many workstations would I have? In theory, the formula will be the sum of the task times. So that would be the sum of all the task times divided by the cycle time. And this symbol, which is straight lines with a ceiling, it's called ceiling, means you always round up, always rounding up. So even if it is 3.2, you make it 4, and so on. So it's not the traditional rounding up 3.5 and above, you make it 4. So ceiling means always round up. That's a mathematical notation. So first we have to sum the time of the task. So we come to this 4 plus 2 plus 1 plus 1 plus 5 plus 3 plus 4. And we get the sum of the TI to be 20 minutes. So 20 divided by the cycle time of 5 and rounding up. Well, we don't have a fraction here. 20 by 5 is 4. So this number is 4 workstations. So we expect with this kind of cycle time to have a minimum of 4 workstations on this assembly line. Now, to design an assembly line using ALB we can do using trial and error. Or we can do using rules. And so in this example, I'm going to use trial and error. Now, your book uses tables. Which are very good and they're very detailed. And to track things, measures, it's an excellent way to keep accurate data of all the measures you're having. But I use a different method. There is an alternative to the book, if you are careful, is to use boxes, as I will be doing in this example. So I'm going to use trial and error and boxes. So as long as you understand it and you are very accurate, use boxes. If you don't understand the boxes, please use the tables in your book. The solutions for the problems given in your book are all using the tables. You can also do the boxes and see if your solutions match the tables. Now, this is the thing with the problems for ALB. The solutions may be different because with trial and error especially, you can have multiple solutions. But cycle time will have one answer and min will have one answer, but the design of the assembly line could be different. Unless you're using rules, of course. We'll talk about that later. So let's do the trial and error using boxes. So the idea is we're gonna design an assembly line. Each box represents a workstation. And in that workstation, we're gonna assign tasks, these tasks. And we know that we have a cycle time. At each workstation, the product is going to spend the amount of the cycle time, which is 5 minutes. So we only have 5 minutes at each workstation to do work before we send it to the next workstation. What tasks can we assign? So we are looking at 2 things here. The time, we only have 5 minutes, and precedence. So we're assigning tasks based on 2 things, time and precedence. We cannot assign a task if its predecessors have not been assigned. So, to start with, what task can we assign in the first workstation? Well, the only task that doesn't have a predecessor is A. So, I don't have a choice but to assign A. If I assign A takes 4 minutes. That leaves me with how many minutes? 1 minute out of the 5 minutes. So then if I assign A, I put a check mark on that. The only thing I can assign, the only other task I can assign is C, right? Because then C is only 1 minute. B, 2 minutes, that'll be too much. So I assign C, and how much idle time do I have on this workstation. 4 plus 1 is 5. There is no idle time on this workstation. Up all the 5 minutes. So I open another workstation, another box, and so now in this box I start with brand new 5 minutes. And now that I did A, I can do B. I cannot do G yet because the predecessors for G are C, E, and F, and I haven't done E and F yet. So the only one I can put in right away is B, and B takes 2 minutes, so that leaves me with 3. Once I do B, I can do D or E, but E is 5, so I cannot really do E. I can only do D, so that's D. 2 plus 1 is 3, and that's it. I cannot do F because F is 3, so I have to close this workstation, and that leaves me with how many minutes of idle time? 2 minutes of idle time. Too much to put in F and too much to put in E because I will exceed the 5 minutes of cycle time. Open the third workstation, and in that workstation I can put F or E, and so this is why it's called trial and error. It's up to me. Some people can put F, and that's correct. Some people can put E, and that's correct. Either layout would be acceptable. So if I put F, that leaves me with 2 minutes of idle time. I cannot put anything else. If somebody else puts E, that's correct too. And then, regardless, I will have to put open a new workstation and put E in it, and that leaves me with 0 idle time, and the last one would be for G, and that would leave me with 1 minute of idle time. So, like I said before, the trial and error technique will have multiple possible solutions. But what you're trying to do is fit as many tasks as you can in a station, because your goal is to have the minimum number of workstations. The more workstations you have, the more inventory you have, and the less efficient you are. So you're trying to fit as many as possible within the cycle time. So by doing this, you've finished assigning all the tasks, and now you come to calculating the metrics for this. What are the metrics of that are relevant for this assembly line problem? Efficiency of the assembly line, that is calculated by calculating the sum of the time that it actually takes the task divided by little n multiplied by the cycle time. Little n is the actual number of workstation. So big N, min, was the theoretical number, and that was 4. But we ended up with an actual number of 5 workstation. So to calculate that, 20 divided by 5 multiplied by the cycle time of 5. And of course, efficiency, we want to make it a percentage, so we calculate it by percentage, so we have an 80% efficiency. This line is 80% efficient. The complement of that, we call it total percent idle time, or another name for it is balance delay. And that would be 100% minus efficiency. So that would be 100% minus 80% will be 20%. So my balance delay is 20%. So the total idle time, total actual idle time, is equal to, I can calculate it, n times ct minus the sum of ti. So that would be 5 times 5 minus 20. And so that 25 minus 20 is 5 minutes. You can calculate it like this and then go back and confirm with the numbers that you calculated under the boxes, 0 plus 2 plus 2 plus 0 plus 1. That is also